Hello, everyone. Our group number is 27. Our group members are really new. 很瑞幸佩瑶你. The post-quantum cryptography is a subject we have selected for this group project. Our focus is on lattice-based post-quantum cryptography algorithms. Firstly, the development of PQC will be briefly discussed. Then we are going to introduce what is lattice, most common lattice problems, and NTRU public key encryption. Finally, we will talk about the potential research areas on post-quantum cryptography. Okay. Modern asymmetric cryptography algorithms mostly benefit from the discrete logarithm problem and the difficulties of factorization of large numbers. However, in 1994, Shor demonstrated that quantum computers can efficiently solve factorization and discrete logarithm problems in polynomial time, which significantly threatens public key crypto systems. Cryptographers are motivated to research on post-quantum cryptography that is resistant to both classic and quantum computers. Post-quantum cryptography could be also called quantum-resistant cryptography. By far, main candidates are lattice-based cryptography, code-based cryptography, multivariate polynomial cryptography, and hash-based signatures. And lattice-based cryptography is the most promising candidate for quantum-resistant algorithms. Then the lattice-based cryptography's characteristics are average case hardness is equivalent to worst case hardness. Then it is proof secure. Third, its computing efficiency because it uses module addition and multiplication based on small integer. Then it is simplicity of implementation because it has very simple algebraic structure. Finally, its computational problems are shortest vector problem, closest vector problem, shortest independent vector problems, and etc.
This is part 2, lattice-based algorithm. First, we should know the definition of lattice. Lattice is integer vector space with a basis vector set. We can say from the following images. The red arrows are the basis vector sets, and it generates the lattice. Before we know the lattice problem, we should know the classification of problems. The first type is P problem, which means there exists an algorithm solving the task that runs in polynomial time. The second type is NP problem, which means there is no way to find an answer quickly, but it is possible to verify the answer quickly. The third type is NP hard problem. It is at least as hard as the hardest problem, the NP problem. Now we know the problem's classification, and we should know the two famous lattice problems are shortest vector problem and closest vector problem. For SVP, it is to find the shortest non-zero vector in a basis of a vector space V. It used to be an NP problem. Now it is P problem. Its variant approximates SVP. With a parameter alpha can control the difficulty of this problem between P problem and the NP hard problem. For CVP, it is to find the vector in lattice which is closest to the basis of a vector space V. It is NP hard problem. And the most prospective lattice algorithms are NTRU public key crypt system and learning with arrows crypto system. For NPRU, there is a simple version of it. Alice chooses a big integer q and a relatively small integer f and g, which should meet the following requirements. Then Alice generates the public key and keep the private key with the formula. Now Bob wants to send a message in, and he firstly chooses a random integer r and generate the cipher with the formula shown in the slides. Then Alice gets the cipher and firstly compute RG plus FM or Q. We can easily know RG plus FM is less than Q, so A equals RG plus FM precisely, and we can easily recover the message with the formula like this. Mathematically, in order to attack this protocol, this is described as, with two known vectors, you need to find a set of linear combination coefficients that generate a factor short enough, which is a lattice SVP problem.
The next section is future directions. First direction is security evaluation of post-quantum algorithms. Security proof for evaluating the security of post-quantum algorithms is crucial. But algorithms like NTRU encrypt still lacks formal security proof. What's more, cryptanalysis of algorithms to find potential implementation problems, mathematical attacks, and set-channel attacks is an important research topic, which can help improve the algorithm's security. The second direction is standardization of post-quantum cryptography. There are different systems and tasks that requires encryption, and a useful standard will provide solutions designed for different situations. In recent years, the cryptography authority of many countries have begun to pay attention to and promote PQC research, but has not yet progressed to the stage of actual system development and the construction of infrastructure, because the algorithms has not yet been standardized. NIST has started developing standards for post-quantum cryptography. The standardization process requires feedbacks on the strength, efficiency, security, and practical applicability of post-quantum schemes. As for deployment, the transition from existing crypto system to post-quantum crypto systems requires significant effort, and it needs to take place well before any large-scale quantum computers are built, so that any information later corrupted by quantum cryptanalysis is no longer sensitive when the compromise occurs. Researchers can focus on these areas to prepare for the planning and implementation of such a transition earlier. As we can see, the cryptography landscape is about to change, and will be more fluid in the future. We need to say goodbye to our rigid and static understanding of cryptography and embrace its new agile nature. Thanks for your listening.